In this example, we're going to use a comparison test to help us determine whether the following series converges or diverges. And now what I'm going to highlight in this example is we're going to try and set up an inequality to directly compare our series to another one. However, the inequality isn't going to work out the way we need logically for a comparison test. So we're actually going to go ahead and use a limit comparison test to come in and save the day. So that's what I'm going to highlight in here. We're going to try setting up an inequality. It's not going to work out the way we need to. Then we're going to lean on the limit comparison test to help us out. So with any of these comparison test problems, the first thing we need to start with is finding a series to compare ours to. So we take our series, 5n over 7n cubed minus 4. And what I like doing is asking the question of, for very, very large values of n, which terms contribute the most in the numerator and denominator? So for large n values, who's mattering the most in the numerator and denominator? And well, in the numerator, there's just that 5n. So we take that on the right-hand side, put it in the numerator. And on the left-hand side in the denominator, well, there's two terms. There's the 7n cubed and the minus 4. And as n is getting very, very, very large, well, that 7n cubed, that's the term that's contributing the most. So we can put it in the denominator on the right-hand side. So we have 5n all over 7n cubed, which, doing a little bit of algebra, tells us we have 5 over 7n squared. So it looks like the series we're going to compare to is the series from n equals 1 to infinity of 5 over 7n squared, which we could write as pulling out a 5 over 7 constant in front of that series, 5 over 7 from n equals 1 to infinity of 1 over n squared. So the next thing we need to do in these problems is, well, if we found the series that we're going to compare to, we need to figure out what that series actually does. So we have this series now of 5 over 7 times the series n equals 1 to infinity of 1 over n squared. And well, if we look at this series, this is a p series. We have 1 over n to some power. In this case, that power is 2. So this is a p series with p equals 2. And 2 is greater than 1, which is a threshold value for a convergent p series. So actually, since p equals 2 and it's greater than 1, this p series is convergent. So we're going to compare to a convergent series. So again, the next thing we're going to try, since we know now we're comparing our series to a known convergent series, we're going to try and set up an inequality. And for us, what that means is, since we're comparing to a known convergent series, in order to make sense of this logically, we need to show that our series is smaller than a known convergent series. So we have our series that we started with, 5n over 7n cubed minus 4. And we want to show that that series for any n value is always going to be less than or equal to that known convergent series function. So 5 over n squared. And again, we haven't shown this is true. This is an inequality that we're going to want to try is showing is true through some algebra. So the first thing we do is see if we can cancel out any terms, make the algebra down the line a little easier for us. And well, we can cancel out those 5s. So now we're looking at n over 7n cubed minus 4. And again, we want to try and show that that is less than or equal to the series function that we know to be associated with a convergent series. So this is, we're trying to show is less than or equal to 1 over 7n squared. So from here, we can do the usual thing of cross-multiplying, doing some algebra, doing some arithmetic, trying to show that the inequality is indeed true. So when we do some cross-multiplication, on the left side, we get 7n cubed. Now on the right-hand side, we're going to get the following, just 7n cubed minus 4. And you might see where this is going now. Well, those 7n cubes we can cancel out. So what we have left is 0 less than or equal to minus 4. And well, we know that this is certainly not a true inequality, that this is indeed false. So this thing is indeed false. And what that means is, well, we can't go about proving that our series is less than or equal to that known convergence series just through a little bit of inequalities. So this is where we have this idea, though, that our series, it should behave a lot like this known convergence series up above. But the inequality just isn't working out the way we need it to logically. So this is where we're going to come in and try the limit comparison test. And what the limit comparison test is going to say is, well, we're going to take a limit of the ratios of our series functions. And if that limit is a finite non-zero number, then both series must do the same thing. So let's go ahead and check it out. So again, the limit comparison test, we take a limit as n goes to infinity of the ratio of our series functions. So we'll take our original series, 5n all over 7n cubed minus 4, divide by our series function we're comparing to, which is 5 over 7n squared. And now we want to show again that this limit, it comes out to a non-zero finite number. And that would tell us both series do the same thing. All right, before we get ahead of ourselves, we're dividing by a fraction. So what we can do is reciprocate that fraction and multiply it on. So we have 5n all over 7n cubed minus 4, our original series function. And now we can multiply by the reciprocal of that denominator fraction, 7n squared all over 5. And we can see a little bit of cancellation happens. The 5s cancel out. We can do a little bit of algebra here. We have the limit now as n goes to infinity of 7n cubed all over 7n cubed minus 4. And well, now we can try evaluating this limit. As n goes to infinity, n is going to infinity, we ask ourselves what's happening in that numerator and denominator. And well, that numerator, the 7n cubed, that thing looks like it's heading towards infinity. And this whole denominator, as n goes to infinity, as n gets very, very large, 7n cubed minus 4, that's also looking like it's heading towards infinity. So what we get to do here is L'Hopital's rule. Again, L'Hopital's is asking us, basically, which is growing faster or shrinking the fastest, the numerator, the denominator. And the way we can assess that is by taking the derivative of each part individually. So the derivative of the numerator, derivative of 7n cubed, that is 21n squared. Derivative of the denominator, derivative of 7n cubed, well, that's 21n squared. And the derivative of the minus 4, well, that's just 0. So now we see, well, we have 21 squared in the numerator, 21n squared in the denominator. Those cancel out. The limit we have left is the limit as n goes to infinity of just the number 1. And well, that 1 has no n's attached to it. So this is just equal to 1. And why this is special, this 1 is a finite non-zero number. And this is the magic of limit comparison test. When we take the ratio of our series functions, just like we did, and take the limit of it as n goes to infinity, if we get a finite non-zero number, that says both series must do the same thing. So I'm just going to write that. Both series must do the same thing by limit comparison test. Or in other words, by limit comparison test, we know both series either converge or both series diverge. So that's what limit comparison test tells us. Hey, both series do the same thing. Now, if we go back to the second thing we did in this problem, we know something about one of those series. The series that we're comparing to, we know that series is convergent. So we can put these ideas together. We know one of the series is convergent, but limit comparison test told us both series must do the same thing. So therefore, both series must converge. So the final conclusion in this problem is the following. Since limit comparison test tells us both series do the same thing, but we know the series we're comparing to converges, both series must also converge, which tells us our series that we're interested in must be convergent.